So last week we began talking about circuits and electric current. And one of the analogies that I continually use is the analogy of flowing water. So if you recall, this right here was a river flowing from the left to the right. There's an island here where the river has to split up into branch number 1 and branch number 2. When I have one single path, we call that a series. We say that we have a series circuit. So I have one location which leads to another, which leads to another, and due to conservation, we cannot lose or gain any charge along the way. So in this case, with our water example, I have 1,000 gallons going by every second. I have to have 1,000 gallons going by every second everywhere, otherwise I get a backup of water and nothing flows. Notice I have gallons per second, not meters per second. Speed and flow rate are different. So I might have a very wide section of river where the water doesn't have to flow very fast, and then I have a more narrow location where, to keep up, the water has to shoot through really, really quickly. And that kind of depends on how wide your river is going to be. So that's when it comes to a series, you are going to have the same flow rate everywhere. For charge, flow rate is coulombs per second, also known as an amp. Now when I look at the river splitting up across two different locations, I have branch 1 and branch 2. If I have 300 gallons per second on this branch, I'm going to have 700 on the other to keep up with my total of 1,000. We call that the junction rule. Coming into this junction right here, I had 1,000. Coming out, I still have to have 1,000, albeit broken up down into two different branches. If I look at branch number 1, even though it's part of a bigger system, branch number 1 has to have 300 gallons per second the entire time. This one has to have 700 the entire time. And what happens when they reconnect? We are back to 1,000. So 1,000 coming in the form of two different branches, 1,000 flowing out in the form of one single river again. We call that the junction rule. If we scroll down and look at some of the notes that are listed here, I have some reminders for you. First, charge flow, current goes from high to low. Our flow rate, gallons per second, for our water analogy is going to be our coulombs per second, or the amp. Current is abbreviated with capital I. And we have our one branch series where our constant current is happening. 1,000 happen to be our example. It has to move really, really fast through the narrows to keep up. When we have multiple branches, that's branch 1 and branch 2, our current has to split up. The wider wire is going to take more current, so if we glance up, it's probably not a surprise that I labeled this one with a big number and this one with a small number. This one has more room. It's going to allow more water to go through. Now, I realize we might have deeper parts of a river, and you might say, Mr. Lord, what if this is really, really deep and can carry just as much water? You're right. We're kind of looking at this just from one angle, trying to keep things simplified a little bit. The bigger the section of river, the wider it is, the more water will flow that way. And so that's what we had looked at previously, and so what we'll look at today is a little bit more of the math that's going to be involved. This was the side view of branch 1 and branch 2. So it doesn't matter what the path is that each of our branches takes, it's still going to start at a particular height and it's going to end at a particular height. They both have to fall through the same amount of potential. So when I look at this, I might have a waterfall on one side and I might have something a little more gradual on the other side. So that's how our two branches would compare. If I scroll down, right, the loop rule says we have to have the same amount of voltage used for every loop that we have. So we have to have the same voltage across each branch. So if I go back to the previous slide here, it doesn't matter how big or small our wires are. They both have to go from a same high voltage location to the same low voltage location. So the elevation of my water, because that's what a river is, moving water from high to low, the elevation of my river is like the voltage. There is the high potential, high voltage, and here it's low voltage or low potential. So everything's kind of consolidated right here. Series means you have one path, constant current, and the voltage is going to be shared. If I skip forward one slide, if I have a 4.5 volt battery and I have 3 different light bulbs that are all perfectly identical, then each of my light bulbs is going to have to use up and share the 4.5 volts that it was given. So I get 1.5 volts falling across each of my light bulbs and they light up equally. This was an example from a worksheet if I had 2 battery packs. All right, I get 2 battery packs, 4.5 and 4.5 gives me 9. There's 9 volts for the light bulbs to share because they are in series, they will share. Now, this right here tells us if they're sharing, who's going to get the most voltage? If I have 9 volts to share, is it always going to be 3, 3, and 3? Well, it depends on your resistors or your light bulbs. What I look at is whichever resistor is hardest to go through has the biggest R value. And think about it, if I need constant current throughout an entire branch and there's one spot that's extra hard to get through, we're going to have to push with way more voltage here than anywhere else. So the hardest resistor, the worst resistor, has to have the most voltage just to keep up. And I'll find some, see if I can get some light bulbs to show a little video demo of the different brightnesses we could get from our different bulbs. But you would find that the worst bulb is going to be the brightest in series. When it comes to parallel, parallel means you have multiple paths. We have to have the same drop in voltage for each path. We saw that with the river analogy, branch 1 and branch 2 going around the island. So they're going to share the current that comes flowing into the islands. Some of it went up high, branch 1, some went down low, branch 2 in our picture. Which branch is going to get the most current? Whichever one is easiest to go through, and that is typically the widest one. So if I look over here, 1 over R. So if my resistance is really, really, really big, 1 over R is really, really small, which means that it gets a small amount of current. So when my R is big, I get a small amount of current. When R is small, the reciprocal of a small number is a big value. So the smaller the resistance, the more current is going to flow through. So the wider the wire, the shorter the wire, more current's going to go through that segment of wire because it's easier. Plain and simple, it's easier. So this right here is just a list of series and parallel. And we kind of glossed through this rather quickly last time. We're going to look at a little more in depth this time. Current is constant. We already said that. Potential is shared. We already said that. We have a relationship here. We just mentioned that. This right here, this equation, we're going to start looking at these equations now. This equation is how you figure out the total resistance of a group of resistors in series. It's easy. You add them up. Quite literally add them up. Think about it. You have one path. Every charge has to go through the whole path. So it has to go through the first resistor, then it's got to go through the second one, and you quite literally add them all up. Added resistors cause an increase in resistance. I can see that right there, very easy, which means that my total resistance will always be greater than any individual one. Series is really easy in that sense. The only thing that's challenging is remembering that the worst resistor gets the most voltage. Sometimes that tricks people. Everything else I think is pretty straightforward. And we kind of mentioned that last week. This one we skipped last week. This one's the harder one. And we're not going to worry about how we came up with the equations. It's kind of easy, but it's not really important. Potential is constant. We said that every branch has to have the same voltage. Current is split up and shared. We already said that. I is proportional to 1 over R. So we did all that already. Previous slide. This is our equation. 1 over the total equals 1 over R1 plus 1 over R2. So the reciprocal of the total is equal to the sum of the reciprocals. And we could do a real quick and easy example of why this is so if we were able to do this in person on a big whiteboard. But basically what this means is that every time you add a resistor, you are decreasing the total. Think about it. Whatever I add up over here, big or small, doesn't matter. Every time I add up a number, this right side gets bigger and bigger and bigger. But the right side is equal to the inverse of our total. So as this number gets bigger, the inverse gets smaller. So what does that mean? It means that our REQ actually decreases. This is my example where I said it's like having lanes of highway. Every time you add another lane, you are making traffic flow easier. Even if the lane has lots of potholes and isn't a great choice, if one car goes that way, you've just made the flow a little bit easier, even if it was just a teeny tiny little amount, one single car's worth. So what we find is that the total resistance is actually smaller than every single individual resistor involved. And that's where we have to have our concern. Last week we talked about fuses and circuit breakers. That's what we have to concern ourselves with. If we put too many resistors in parallel, pretty soon REQ gets really dangerously low. And you say, well, low REQ, why would low resistance be dangerous? A low resistance translates into a very high current. And we talked last week, current kills. Current is what causes damage. Whether it's humans or to devices or metal, current is what causes the damage, not voltage. Everyone says danger high voltage. That's actually wrong. Danger high current. But the current is affected by your resistance. So if I have lots of resistance, that's good. So the more resistors we have in parallel, the lower our resistance becomes total. Each individual resistor is fine, but the total coming in from your source gets really, really high in terms of your current, and that's dangerous. So here are some pictures on how you would design a parallel. Parallel is how everything that you are associated with, everything you've ever seen, it's all parallel. I've heard people always say, oh yeah, old Christmas lights. I am old. I have never had Christmas lights where one went out and they all went out. It's very inefficient. It's very impractical. I'm not saying they don't exist. I'm saying I've never heard them, even though everybody says that they are out there. So this is how we would draw a parallel. Nice and simple, right angle bends everything. This is how they're practically put together. You wouldn't have a wire splitting up, because having a wire split up, that's difficult to make in real life. So what would you do? You'd have a wire touch one side of the light bulb, and you'd take another wire on the same side of the light bulb and you'd extend it out to another light bulb. So think about it. If I have a charge, if my little mouse is my little cursor is a charge, my charge gets to right here, and my charge can either go through the light bulb and light it up and then go back to the other side of the battery, or I have a charge that could go here and continue along. Charge can't be in two places at one time. Each individual charge, it's like a molecule, right? A water molecule can't be in two branches at once. So my charge is either going to go through the light bulb and light it up, or continue through this light bulb and light it up. So that's practically how you would design it. That way you don't have to have any breaks in your wire. You just have this metal wire touching this metal side of the light bulb, touching the next metal wire, and we know when metal connects, it acts like one big chunk of metal. This right here is how it's actually done in your house. You actually buy a big wad of wires. It's wrapped up in white insulation, kind of an off-white insulation, and inside you got a bunch of wires. So what do? You cut off one end, you pull the wires out, and you connect it to your battery or whatever your source is. And then this literally runs through the walls in your house. And then you get to where you want a light bulb, you cut the wire, you pull out the ends, and you connect them to the light bulb. And then you take another segment of this wire, cut off the end, connect it to your light bulb. You send this through the walls of your house. And that's how it works. Now, it used to be that code for the house would require you had to have one wire, which was the hot, which is kind of like your positive, and one separate wire for your negative, and they had to be like 12 inches apart or something like that. And they realized eventually that it wasn't necessary. It was not very cost effective. It was much more challenging to build things, and so now it has been changed up, and now we have something much more efficient. So this right here we showed last time. This was an example. If I have a bunch of resistors all connected in parallel, if I have a 12-volt battery, that means 12 volts goes through this resistor and this resistor, etc. And if each of them has a convenient number of 6, okay, then that means 12 Here's my Ohm's law, V equals I times R. So 12 divided by 6 is 2. I've got 2 amps going through here, and here, and here, and that's not a big deal. The big deal is when they all come back together. 2 joins here for 4, for 6, for 8, and now I've got 8 amps flowing through part B. And maybe 8 amps is too much for this wire. So instead of having my wire melt somewhere and cause a fire perhaps, I put in my fuse or my circuit breaker, my device. This is my designated weak spot. I have this here. Maybe this is designed to fail at 8 amps, which means if I go one more, this thing's going to fail, and it's not going to let my wires get damaged. We can use a fuse, which is cheap, but you have to replace it. Or you can buy a circuit breaker, which is more expensive, but is reusable. And we did that on last week's episode, so to speak. We talked about circuit breakers and fuses, and I went through my house and I found you the circuit breakers. We went to my car and found the fuses. So we have our equation here, review from last week for resistance. We have our electrocution, voltage is known. Current is what varies and is what hurts us. Luckily, our dry skin is a high resistance. It's wet skin that is a concern for us. So if we have a malfunctioning circuit, wet skin would be dangerous. If everything's functioning properly, nothing is going to go through you, and you're going to be just fine. You don't have to worry about, oh, I can't turn a light switch on because I have wet skin. You're going to be fine. But if there's something malfunctioning in your house and you touch it while wet, yes, the possibility of that high voltage electricity running through you into the ground where the voltage is 0, things always flow from high to low, it could definitely flow through you, and that is a concern, especially if that electricity flows through your heart, because it causes your heart muscle to flex and never relax. And if your muscle flexes the whole time and never relaxes, it can't beat. And if it can't beat, you don't get blood flow. So there were some examples there. So this shows different brightnesses. We'll do a little video demo, and I need to find the right devices. But here we have something in series. This right here was the worst of our light bulbs, but it was the brightest because it needed more voltage to keep up. When I come down here, R and L, this one was brighter because it's a thicker wire. It allowed more charge to go through, same voltage, more charge, and so what this did, this allowed us to come up with our power equation. Power is watts, watts is joules per second. How much light's energy, how much energy is given off every second. And we talked about how to calculate your electric bill. I showed you my electric bill. We went through all the charges and all the costs. So if you didn't watch last week's, jump to the end if you have to and take a look at how all of that works, because you will all be paying an electric bill sometime in your life. That's the box where the electricity goes in, and as we already mentioned, you've got your energy. You can do watts times a second equals a joule, but that's really small. And so you'd have, like, thousands and millions of watts. That's not very convenient when it comes to calculating your bills. So they use kilowatts, which is bigger, and hours, which is bigger. And the numbers are much more manageable. So for me last week, I think it was, we found that I used up like 342 kilowatt hours for the month, and they could charge me accordingly. Now, this is the new part here. To solve our problems, number one, find Req for the circuit that you're using. Find the total current. Usually you're told what the battery is, and usually you're told all the individual resistors, and you found Req. Find what the total current is. So V equals I times R for all my totals. Then you have to ask yourself, is this thing series or is it parallel? Once I know if it's series or parallel, then I know which of my values, voltage or current, is the constant. I come down here, I plug it in with individual resistors, and I find all the rest. This part, relatively speaking, is hard, easy, hard, and then step 4, if you're asked about the power of each individual device, that's plug and chug, easy. So it goes hard, easy, hard, easy. You're not always asked about the power of an individual device, but if you are, you're already going to have V and I, plug and chug. It's quick and it's easy. So this right here is a slide that has two side-by-side examples, a series and a parallel. They both have a 3-volt battery. Please forgive the sloppiness of my drawing. Drawing on my computer instead of on my whiteboard is definitely more challenging. So I have a 3-volt battery, and I have a 6 ohm and a 12 ohm resistor. These are connected in series, one single path. These are connected in parallel, two different paths. So I'm going to look at them, we'll solve them both, and then you can actually see a side-by-side comparison. So looking at the series first. Number 1, find REQ. A series is easy, add them up. 6 plus 12 is 18, done. Find the current. Plug and chug, this is quick and easy, done. 0.17 amps. Now, series. This is in a series. I know that I is a constant. So once I've calculated 0.17 amps, I can come down here, and what I like to do personally is I write down each resistor that I'm going to use. 6 ohms. Put a line under it. I know its current is going to be 0.17 amps. I know the resistance is 6. Plug and chug, and I get 1 volt. Here, 0.17 amps times 12, 2 volts. And I double check, and I can always double check my work by adding these up. 2 plus 1 is 3. That's the voltage that I had total. And my loop rule says that these two should add up to whatever the battery gives me. Battery gives me 3, I use up 3. Now if I cared about the power of each of them, simple, bring it down, plug and chug. So I calculated 1, I calculated 0.17, do the math. I calculated this, do the math. It's quick and it's easy, so I can see what my power output is. Now when it comes to our problems, parallel are always going to be a little bit more challenging, just because the math's a little bit more challenging. So the first thing, find REQ. Well, I got to add up my reciprocals, 1/6 and 1/12. That's 2/12. And 1/12 is 3/12 is 1/4. Common error. Students get to 1/4 and they think they're done. 1/4 is the reciprocal of your answer. So here the numbers we chose were nice. Oftentimes, like on a UT assignment, they're not nice. So you have to use your calculator, you got to use parentheses, you can use the negative first power button on your calculator. Long story short, the REQ is 4. Notice 4 is less than each of them combined, each individually. So I actually have a lower total. Compared to a series, it's way different. So I have less overall resistance. That means I should get more current. So when I come down here, 3 volts given to me, 4 ohms, just calculated that. My current is 0.75. Notice the big difference, 0.17, 0.75. So I've got way more current flowing out of my battery. Parallel means that the voltage is constant. Notice the difference. So 3 volts goes through the 6, 3 volts goes in the 12. So if this is my 3 volt side, I got 3 volts on the top side, and this is the negative end of my battery, the 0 volt side. So I got this as the 0 volt side. So this one goes from 3 to 0, this one goes from 3 to 0 also. Now this is different because we talked about the loop rule, right? We said that the battery, whatever the battery gives, has to get used up. And I can understand someone saying, wait, it's giving us 3, but we're using up 3 and 3 for 6. That doesn't make sense. Remember that it's called the loop rule. Each individual loop has to follow the loop rule. So I gained 3 and I used 3 and back I go. I gained 3, I used 3 for the 12 and back I go. So that's how it works for each individual loop. One of the analogies I used was a water slide. You climb up the steps of the water slide. I can use 1 set of stairs, 20 set of stairs, doesn't matter. I get to the top and I have lots of choices. I can take this route down, I can take the red slide, I can take the blue slide, I can take the pink slide, and every slide is going to fall the same amount regardless of what type of slide it is. It's going to fall the same amount because I walked up the same set of stairs. Hopefully that helps. So we come down here, parallel. Voltage is a constant. So instead of bringing down my current like I did here, I'm going to bring down my voltage, 3 and 3. And now what I'm going to do is calculate I. I get 0.5 amps and I get 0.25 amps. And I can double check my work. These two numbers added up gives me 0.75. That's the total. So I can use the junction rule. Remember, the junction rule said that all the current flowing in has to equal the current flowing out. So if I have right here 0.75 coming in and I've got two different branches going out, those two branches have to add up to 0.75. So the convenient thing about both of these is there is a built-in check your work, make sure you're correct type of method. I can add these up to make sure the voltage matches. 1 plus 2 is 3, and that follows the loop rule. I can come over here, add up my currents, get the total. That's the junction rule. And when it comes down here, I can look at this right here and I can figure out my power. Notice how much extra power I get out of this system than this one. And that's another reason why nobody uses a series circuit. Besides being inconvenient, problem with the series, if one goes out, the whole thing fails, right? If I go up to the top here, if this bulb burns out, there's a break in the wire. If there's a break in the wire, the charges cannot flow and everything goes out. So besides that being extremely inconvenient, if this bulb burns out, there's still a path for the 12. So this is how your house is wired. If one thing is broken, gets turned off, bulb goes, whatever, everything in your house keeps working. So besides the convenience factor, the other reason here is if you connected everything in series, it's going to share the voltage. Instead of everything getting its own voltage, it shares the voltage, which means that everything's going to run way dimmer than if you would have just connected it in parallel. Now, the last example here that I'll mention, you can go through the slides and we can talk about it in person on our Zoom meetings. I call it the family tree. What happens if I have a series parallel combination? It can happen. A combination of series and parallel. So maybe I've got one branch that splits up into two branches, and maybe each branch has a couple things in series. So what you do is you simplify your drawing. I draw it with junctions or devices. I'll show you in just a second. And then I combine devices. I start small. And then notice what I have here. Step 1 was finding REQ. I said, remember, step 1 was the hard. That's what I do. Step 2 was finding totals. That's easy. That still works out the same. Step 3, finding the individual resistors. That was hard. I'm going to use the family tree method. I start big and go small. So here I start small and go big. Here I start big and go small. I'm going to explain exactly what that means in a second. Step 2, easy. No need to point it out. Step 4, easy. No need to point it out. So step 1 and 3 are the hard ones. That's how you're going to modify it. So here we go. I have a 2 that is in series, right? Everything has to go through the 2. And then I get to point A, and it splits up. It goes down one branch or the other. I now have a parallel. Look at this parallel. This parallel has 2 in it. It's in series. So I'm going to redraw, because if I don't recognize what I'm looking at, I can't do the problem very well. So I redraw. So what I do is I draw my wires going from left to right. So the first thing I get to is the 2. I draw it. The next thing I get to is a branch at A. I restructure the branch so that I have one branch going up and one branch going down. One of those branches has a 6. There it is. One of those branches has a 4 and an 8. There it is. It reconnects at B. I think this picture is probably a little bit easier to deal with. And as you do this, as you practice, you're going to do these things. You're going to do it as much as you have to. If you can look at this and you don't need to redraw it, then you don't. Don't waste your time. So I said that I combine the smallest things first. So I look and I ask myself, what can be combined without affecting everything else? And I find these two right here. These are the ones that are tucked into the most, right? I have a series with a parallel with the series inside. This is the smallest thing right here. So I add them up, 12. I call that RA. I use letters personally. RA, RB, RC. So there's RA. And I literally redraw. Since this one is calculated, I call it RA is 12. Now I can connect these two in parallel. I do my math. I get a 4. So now I can redraw. And you might get to the point where you only do half of these drawings, then you stop with the redrawing, but that's up to you. There's a 4. Now I got a 2 and a 4 for a 6. So all of those combined together behave like a 6. Notice I call this one REQ. I used RA and RB to get to this point. There's REQ. What's step 2? Step 2 simple. V equals IR for my totals. Simple. Now, how do I... Uh-oh, did I not... I'm sorry, so that's how I do the redraw. So now, here is another example here. So you can see how I combined the series, the parallel, and then the series again. All right. Step 2, finding my total. So you can look through these slides. They are posted. Here's the family tree. I'm sure other people do this, but I've always been using this one. I call it the family tree. You're not going to find the family tree method in your book, at least not by name. Here's my total. So you remember the family tree, I start big and work small. So what's my total? And then I ask myself, I look at the previous picture, and I start with the biggest. So I start at the end. I had 3 things connected in series. So I write down literally series. This was made up of a series of 3 things, a 560, a 560, and RB, which was made up of everything else. All right, go back a slide, and I look. There's my 560, and my RB, and they're connected in series. So what do? I bring down the current. Current is constant in a series, so I bring out 0.095 here, and here, and here. I plug in the R, 560, 148, 560. I do it, and I get all these voltages. If you add them up, you get 120. You can trust me on that one. I checked my work. 120 is what I should get. Good. So now I can take this one, I can break it up. What was RB made up of? If you forget, you go back a slide. RB was made up of these 2 things in a parallel, a 200 and a 570. So there it is. There's my 200, there's my 570. They're in parallel, which means that they're going to share voltage. They're not going to share the 120 volts. They're sharing the voltage of that particular branch. So 14.1 gets pulled down here, 14.1, 14.1. Using R that's given, I got my currents. And the last one is RA. RA was 2 in series, so I bring down my current, 0.025, 0.025. And I'm getting one step ahead of myself. Double check your work, add up your currents, and you should get the current that we have out here, 0.095. So besides rounding numbers off, it works. And last, my series. I plug in my currents as a currents constant, so I bring them down here using my resistors, and I get 2 voltages. Add them up, and I get the 14.1 total from the previous generation. So that is the family tree method to solve for a mixed or combination circuit. There'll be worksheets that are available with answer solutions as well, so feel free to check those out as often as you need to. Now, if we kind of continue on here, there are some other pictures that you can kind of go through. Whoops, apologies. So whether it's combining crazy things like this, looking how a voltmeter works, and some previous questions, there's other examples on here that you can go through. Fuses, short circuits, and everything. It's all on here, so feel free to go through as much of those as you want. This right here is how the electricity in your house works. Similar to using a battery, but a little different, so it's all there for you. So drop by the Zoom meetings and we can discuss all those things as we typically do.